While people are getting seated, and before I dig into the meat of the talk, I know there's a lot of interesting talks going on, and there's a lot of options you might want to look at. So here's a few of the things that I'm going to be talking about today. And what the overall talk of is about holistic Redis performance in a very high-performant environment, where high-performant is about high transaction rate, lots of clients, fast speed, and trying to keep your services up. So if that's what's interesting to you, you're in the right place. Again, for the people filing in, we have some seats up here. But I also want to give you a chance, if you don't have a lot of Redis experience, this isn't really a talk towards beginners, so we'll do our best, but feel free. I will not be offended if you feel like it is not the talk for you. And with that, maybe some introductions are in order. So we'll start with me, and who am I? Right now, I'm a software architect with GoPro. I've been building various kinds of distributed systems now for over 10 years. It's probably been about 4+ years now since I started working with Redis. And I've built several very high-performant apps using Redis. And when I talk high-performant, some of the systems that my colleagues and I have built do on the order of 25 billion operations a day across multiple data centers. So we're talking about some big systems. And just some places I've been at previously, Apple, Netscape, Flickr. You've probably heard a few of these. So who are you guys? What are some of the applications that you're building? Anyone? Story view counting. And what kind of a transaction rate do you need to support? 400 or 400,000? Great. How about someone from the back? What kind of apps are you building? Anyone from kind of way back? Any volunteers? How about one more volunteer? Great. So hopefully we have a lot of common interests, and hopefully you can learn some things from me, and maybe the group can learn some things from you as well. So what do I mean? And we've gone into this a little bit, but what am I talking about when I'm talking about high performance? Generally for me, what I'm talking about is a large number of clients and a high transaction rate, low response time, and high availability. So there's a lot of things that you need to build out to kind of make this happen. You'll notice one thing that's not on here, and that's durability. So a lot of what I'm going to talk today is about performance and availability and dropping some of the durability guarantees of a system to ensure that you're still up and you process your data fast. Now, this is a really important consideration. Is this right for your app? For most of the apps that I built, this was the right choice, but it may not be the right one for you. I still hope you'll find a lot of value in the talk, but always keep in mind that I'm talking in some generalities, and what works for one application doesn't always work for everyone's application. So a lot of what I'm going to talk about today sort of falls into sort of three main categories. There's clustering and failover, which I use to support a large number of clients and a high transaction rate, the low response time, and high availability. You kind of get a lot of just from doing clustering, you get kind of a lot of the things you want out of a system. But there's some other things you can do when you start diving into the system, tuning the system both at the Linux level and the Redis level to get better response time. There's also some programming techniques you can take advantage of to, again, increase your transaction rate by dropping your response time. So we're going to start with clustering and various ways you can cluster Redis for performance. And again, as I mentioned, these are kind of the features we're trying to get at by using this technique. The first thing is basic sharding. How many here actually shard their application already? And just really quick, what kind of sharding are you using? Or how are you doing your sharding? Client-based? How many people are client-based? A few of you, Twem proxy? Many of you, custom homegrown code? Anyone? We've got one. So a lot of you are probably familiar and already using this technique. For those of you who aren't, what sharding is basically you split your data across multiple nodes. You send reads and writes in the basic model of sharding that I'm talking about right now. You send reads and writes to the same node. Your node is generally determined by some function on the key, although there's other ways you can do it. And it has a few nice properties, but also a few trade-offs. For this to work well, for your system to perform, you generally need a uniform workload. So if your workload is not uniform, what will happen is you will start to get hot shards. How many people have spent late evenings fighting with hot shards? You got a couple, 3 over here. How about hot keys? Have you run into a single hot key? Yeah. So when your workload is not uniform when you're doing sharding, you often lose the benefits of setting up shards. Sharding is great for single key operations, but when you have a workload or queries that you want to do that involve traversals across multiple keys, those can start getting expensive. What used to be a single server operation can now span multiple servers, multiple nodes. Your data in a database world, and I come from a database background, so I talk a lot about queries and kind of use that language. But essentially, the data you all want to collect or join is distributed across multiple nodes. You also have an issue with node loss. So when you lose a machine, what happens? You have roughly one end of a complete outage, depending on what you're doing. There are other techniques that we'll talk about a little bit later that you can use to smooth this over. But at some point, when you lose that machine, what happens? Hotkeys, as we mentioned, can also be an issue. Is that if you have a particular single key in your system that tends to be hot, and I've worked with systems where we've had, say, like 3 or 5 keys that are extremely hot that every single client is trying to access, it can cause serious performance and workload issues. So another way you can look at splitting up your data across multiple systems is to use what are called read-write replicas. Now, Redis provides a way that you can very easily set up a read-only replica of a master Redis node. And this works really great for a lot of different applications, particularly if you have a lot of reads. So if the ratio of your reads to your writes is very high, this might be a technique to use rather than doing just straight sharding. One of the other ways is that as your read load increases, you can manage that by scaling up your secondaries or your read-only nodes. And all of this is built into Redis. So there's very, very little for you to actually build. It's just config flags. And it's config flags you can add on the fly. Now, there may be, as you unroll this, there may be some issues or trade-offs that you run into that require you to make some changes to your client. One of the things that you now suddenly have to deal with is what's called replication delay. And now, the data that is on your write master, there's some time delay between when it hits your read master, or your read-only nodes. So you basically have to take this account in your programming model. You've essentially lost what's called read-to-writes consistency. So if a process writes and then reads from the node, you may not get that data back, which makes for a very difficult and often buggy programming model. So there are things you can do like pinning to get around that. And then what happens in this model with node loss? It's going to depend on the node. If you lose one of your read nodes, you're just, you're kind of lost some capacity there. You lose your write node, your system's dead. A system like this makes it very easy also to scale up hotkeys. You just figure out which node happens to be hot and dump a couple more read replication or read replicants in. But again, it adds some pain, but there are definitely, it's a very good way for certain applications to scale up or partition their data. Another way you can actually partition your data which is what I kind of call the weird one. And there's no support for this out of box, so you're going to be building a lot of this, is building out a 2-node duplicate. So you basically do writes to both of the nodes. Then on your read side, you issue reads to both of the nodes and take the value that you get back first. So this gives you a lot of high performance on your reads, but it slows down your writes. In fact, when you look at the trade-offs, high performance reads, but you get significant client coding issues, consistency. Most people here are familiar with the CAP theorem, and when we talk about data consistency, how you want essentially your writes to be replicated across your entire system. Well, consistency's kind of just gone out the window when you do this. There's just no really way you can guarantee that writes are always going to happen to both nodes. Node loss, depending on what you do in the case of node loss, can really affect what happens and how your system has to perform. And of course, your costs are now suddenly doubled for every node you have 2. This is one approach. This is kind of almost an approach of last resort. If you get here, I'd actually kind of be surprised. But it is one way, yet another way of splitting up your data to get certain performance characteristics out of your cluster. And of course, there's hybrids. I mean, it should be very clear to everyone that you can take sharding and read-write replicas or sharding in multiple nodes. And again, like I say, multiple nodes is really a technique for me of last resort. Now, you've got your shards, you've got your cluster. At some point, you're going to want to scale up. How can you approach scaling up? One of the ways to do this is scale up horizontally. So lots of smaller nodes versus vertically, a few larger nodes. Always think about actually using multiple Redis instances per host. One of the things that we found is that generally with the single-threaded nature of Redis, you're better with several smaller instances running on a multiprocessor box than basically putting one big instance on there. You're not going to take advantage of all your CPUs if you do that. And also, depending on what OS you're using, you can usually pin one process to a CPU, so you're not getting a lot of context switches between your process, and you'll really max out what you can get out of a single box. As we mentioned, using read replicas for dedicated shards or hotkeys. So if you have maybe one particular shard that's very hot, you can always put in a number of replicas, maybe not your standard number, the same with hotkeys. And when you do this, make sure you automate the deployment and configuration, because managing multiple boxes is expensive. But if you've actually built out the tools to maintain this, it becomes a much easier and faster way to scale out your system. If you try to scale it out manually, you're basically not going to be happy. So let's kind of pause for a second in the happily ever after category. And what are some properties we've definitely hit? Well, we've definitely hit a large number of clients. I have never seen a system with a large number of clients that does not scale out. It does not require you to scale out the number of Redis instances. Just in practice, it does not work well to send tons of clients against a single Redis instance. We've also definitely looked at the high transaction rate, because you've got multiple nodes which can basically provide for a large workload. We've definitely talked a little bit about high availability, at least the basis of it, and we've done something towards low response time, but there's still more to do. So let's start building on this and talk about failover. With Redis, you've largely got kind of a failover. So now you've got your big cluster built out. You want to keep it up because you've got lots of traffic to it. If it goes down for somebody who's got 400,000 transactions a second, that's a lot of data to lose. Now, if you're relying on a human to bring this back up, even in a 24/7 staffed NOC, you're probably looking at a minimum response time of 10 to 15 minutes for a human to be able to address a system failure. And it's assuming that they can do more than just page the next level on call or an engineer. So when you're doing this level of transaction processing, you really need to have automated systems if you don't want to lose data. Out of the box with Redis, you basically have two options. Neither is perfect. I actually think this is an area where the open source community could really greatly improve. This is also pre-cluster, by the way. So we're talking about Redis 2.0 here. We're not talking about Redis 3.0 with clustering, because how you want to approach that is differently. And that's not something I've worked with enough to feel comfortable telling you what to do. So you basically have, for your out-of-the-box failover systems, you've got Twin Proxy, and you've got Sentinel. And who here, I know we had some Twin Proxy deployment. Who here has deployed Sentinel, or who uses Sentinel? We've got a few. Love it, hate it, both? Great. Anyone else? Love it, hate it? Yeah, I think a lot of people. Sentinel, it's nice out of the box, but particularly if you have a complex configuration, sometimes it doesn't scale well. And there's definitely work that could be done on it. But for those of you who have very simple systems, this might be a great way of getting failover without needing to do a lot of work. The thing with Twin Proxy is Twin Proxy generally supports failover by redirecting traffic to a different node. So this, depending on your app and the way you're using Redis, could cause you some problems. Because you're suddenly, and usually what most people use is some type of consistent hash like Katama. So you were talking to node A suddenly and wrote some data here, and Twin Proxy, because this node has failed, has now moved you to node B, and all your data is lost. So Twin Proxy works really well in a caching situation, where if you make a cache hit, you can just reconstruct the data from first sources. It does not work well if you're using Twin Proxy and Katama to do essentially persistent data on your nodes. So when you set up Twin Proxy for failure, you have to really look at what your failure case is, what your configuration is, and what do you need to do about persistent data. And now just to be very, Twin Proxy does not migrate data. So if you lose a node, you have lost that data to whatever backup plan you have. The second way of potentially doing things out of the box is Sentinel. Now Sentinel is based on the idea that you take a read node and promote it up to master. So you basically lose less data. You essentially do a shuffle. Now, again, remember replication lag, so there may be a little bit of data in there. The other thing that we found in practice in our networks is Sentinel failover takes about 4 to 6 seconds to execute, and this is in a top-tier data center, dedicated hardware, big company. Your performance on AWS is likely different. So again, now depending on what your window for failure is, this may or may not work. Now, if these two don't work, you're kind of in roll your own territory. It would be awesome for somebody to roll up something even better that we could all use. Okay, so with that, we've kind of covered the high availability part. We're getting closer to beer. But there's still more we can do, particularly on making our response times fast as possible. And for some people, this is important. One of the systems that I worked on, we really needed our entire operation from client to Redis to back in under a millisecond. So you end up doing a lot of things to try to squeeze out everything you can to get it fast. Largely when we talk about tuning for performance, there's really 3 things that I look at. I mean, you can completely go down the rabbit hole with this, but largely the 3 things you kind of look at are network tuning, the persistence settings of Redis itself, and potentially the small aggregate data settings, kind of the 3 places I would start. Network tuning, these are all various properties of the Linux kernel that you can use to tune the performance of your Linux machine, your kernel, your network stack. This is kind of the basics. You can completely go down the rabbit hole in this, and there are people who are far more experienced at this than I am. But one of the things, if you have a very, very busy server, you want to look at your local port range and make sure you're not having any conflicts, and make sure you have enough local ports to support your number of inbound connections. You can play some games with recycle and reuse on connections, and this has to do with how fast the kernel releases an inbound TCP connection. Again, these you kind of have to be careful with them. You can also increase the number of connections that are basically allowed to a process. And the reason I say you need to be careful with them is that you can hide other problems. You can jack up your port range, or basically drop connections early and hide latency issues within the application itself. So like anything in performance, you really want to tune, measure, basically come up with a theory as to why this works, validate your theory as much as possible, because you could, if you do the wrong thing, actually end up kind of screwing yourself in the end. These network tuning features are also mirrored in the Redis configuration log itself. So from Redis, you can control the backlog, your TCP backlog. How many sockets, incoming sockets, do you stack up on an accept socket before you start rejecting connections? And you can also play with TCP keep alive if your client supports it. Then the final tuning thing I talked about was the small aggregate data switches. And what this is this basically lets you set some limits on the size of your structured data. And by limiting the size of your structured data, you're actually able to represent it in a much more compact fashion in memory. This actually, if you can keep things compact, you actually get a lot better performance out of your Redis. It's like most applications. The less memory you use, it just, you save yourself a lot of problems. And I forgot to talk about persistence. How many people use persistence with the Redis? What kind of persistence? Which mode?
AOF most of the time, and use RDB for backups.
Okay, how many people here use RDB for backup? Rick, more? More, please? Maybe you don't need to back up your data. That's one of the mechanisms that Redis provides. How many people use AOF persistence? Okay, it looks like almost more people are using AOF. Why do you use AOF? Really? Actually, that's not true. It actually is faster in a lot of cases. But there's also this problem. So the way RDB works is it does a fork and then saves off your data to disk. One of the things we found with AOF is that depending on how you've configured AOF, so basically your fsync policy, whether you write to disk, AOF generally happens on the execution thread. So you can actually drastically increase your top percentage latencies by turning on AOF. And depending on how fast you're writing with AOF, more writes is more AOF disk persistent. So it's definitely, in terms of speeding up Redis, it is one way of doing things, but like almost everything in Redis and software in the performance world is you're making a trade-off for faster startup times that may or may not, I don't know the details about your application, may or may not affect persistence down the road and latency. Sorry to pick on you, but thank you for sharing information about your application. For our application, this actually caused an outage. Is that we were running so much data through it, and we had AOF turned on because we wanted to be good citizens and make sure we captured all our changes, that it actually slowed the system down to a point where it collapsed, which is not fun, particularly when it's about 6 a.m. in the morning and you're getting a call about this. So there's all these ways that you can both benefit yourself. You're trying to be a good citizen, make sure your data is durable. Then down the road, you've killed the performance of your app. And that's kind of the message I would send out to everyone, is everything you do is a trade-off, and you have to understand why you're doing it, how it impacts your app, and what are both the benefits and the negative side effects. So let's bring up the dog again. because dogs are always about happy ever after. So we've got the high availability stuff. We've definitely addressed a lot more on the response time. So we're definitely better with our response time. We've tuned our Redis. We've tuned our OS to be better responsive to a high volume of transactions. What can we do on the client side and programming techniques to also speed up the performance of our transactions? Now, this is where a lot of the things that we talked about already can be done to some degree or another transparent to your client. So if you put out a TWEM proxy, you can get a lot of sharding without actually ever changing your client. You have to be mostly, because there are certain operations that TWEM proxy won't handle, or if you basically give it an operation where the keys are split across multiple shards, it will reject it. But for a large number of applications, you can actually drop in TWEM proxy, fairly transparent to the client, and implement a lot of this, the sharding and things we've talked about. But now let's dig in, and you can do a lot of the OS tuning independent of the clients. That one in particular, they don't tend to see a lot of. So now, digging into what can we do on the client side to basically improve our performance. Well, there's basically three key areas here to consider. It's how you manage connections, connection management, your transaction structure, and here I'm using transaction in a very, very general sense. What's the sequence of operations that you do when you make a connect to your Redis instance? Do some operations, some reads, some mutates, whatever. How is that structured? I'm not talking about necessarily the Redis transaction primitive or transactions in the database sense. Just what's your operation doing? And finally, actually, if you think about how you lay out data, beyond just sort of the small data aggregates, how you lay out data can actually affect how fast your Redis operation will perform. So connection management, what are the things we can do here? Well, basically, again, kind of three. There's persistent connections, operation pipelining, and connection pooling. TWEM proxy folk, how many of you basically do operation pooling or operation pipelining through TWEM proxy? Anyone? A couple up here? Again, as kind of just almost the concurrent sort of underlying theme of the talk is, this is great, but in this situation, it doesn't work. I've run into some pipelining issues with TWEM proxy, even though I normally use it. So essentially, when we make a connection from a client to our Redis box, and particularly if we're talking large number of clients, and some of the systems that I've been building, we easily see on the order of 4,000 plus LAN clients that all fairly simultaneously come after the Redis system. Setup is expensive, then you leave a lot of connections in time wait. So having persistent connections lets you reduce the latency. It also kind of, you need often do some server tuning to do this, but it generally kind of, it takes out the overhead, so you're largely just about the operation. Operation pipelining is basically a great way to speed up. If you go read the Redis benchmark, you'll see they get almost a 5-6x speed up just by turning on pipelining in the benchmark. But it comes at the cost, is that you send 3 operations, then you get success, failure, success back. What do you do? How do you handle that? Something failed in the middle of the operation that you're trying to do because you're sending and then failure doesn't come back, it comes back asynchronous. And then finally, connection pooling, if you're using, particularly in almost any Java driver, it's basically, just a specific form of persistent connections. Again, you get the reduced latency, but you need client support. And you have to deal with making sure if there are different operating principles or contexts of the connection, how are you enforcing those? If you're sharing them between different ones. So, which leads us into transaction structure. Definitely how you structure your Redis transactions will affect the performance of your system. If you go towards smaller, you generally tend to get lower latency, improved responsiveness, but you reduce your throughput. And if you're using AOF, a large number of small transactions can have a potentially negative effect on your disk persistence, depending on how AOF is configured. Essentially, it's writing more and more smaller changes. The flip side is you can go with larger transactions. You generally have higher latency and reduced responsiveness because each time a transaction comes in, it takes 2x, 3x, 4x before it's done and the next transaction comes in. So you just naturally get a little bit of reduced responsiveness out of the machine. But you can often increase your throughput. So which is more important for your application, responsiveness, throughput? It's not something I can answer for you, but it's things that you need to think about and trade-offs that are implicit in your system and that affect your performance and how your app performs, and ultimately how your users experience your app. So the last thing you can also do is look at how you actually structure your data in memory. And this, surprisingly, particularly with certain things like lists and certain list operations, can have a big impact on your performance. So one of the things, these are general rules of thumb. Again, please measure, please understand, please put this in the context of your own application. Don't just apply it. But generally, what I've found is smaller structures are better than larger structures. I can get, with a very simple Redis, even just running on this laptop, lists of millions and millions of keys. That's actually going to give me a performance hit down the line if I'm trying to pop off the first key. As a general, and again, this is where you want to find balance, though, because too small, too large, find a good balance. So I often suggest if you can internally shard your data, that's a great technique. So if you have a list that could naturally grow to 100 million keys, Redis will support it, no problem. But if you can actually somehow internally split that list into 10 or 20 smaller lists, you're probably going to get better performance out of your system. In terms of your memory usage, so we talked about letting Redis store things more densely, but can you store things more densely? Can use bitmaps, vectors, something to basically replace strings. Strings are not a very efficient coding of some things. You can very much densify your strings. For most apps, some apps can't. Also, again, moderate size structures. The other thing, if you can isolate the modifications, either by reducing the size of the modification, so you're making more smaller modifications, dropping keys instead of mutating them can often be a way of squeezing out some performance. And again, just be careful, because if you're using AOF, how you mutate has a very big effect on what happens at the AOF level. So we've got our properties. Let's party. So what about your system? So I'm guessing for many of you, you work in maybe a smaller environment. Some of you are definitely doing transaction rates similar to the systems I built. I think some of you are probably in your growing stage where maybe you're doing a few hundred transactions a second, but you want to understand how you're going to grow that to 1,000 to 500,000. So what I would hope you take away from today is, again, all environments are different. I'm giving you some general principles, some ideas, and some things to think about, but your app and what you do with your app is going to be different from what I need to do with my app. Unexpected latency in your system, and this doesn't necessarily have to be from Redis. This could be the thing downstream from Redis that is processing what your clients are shoving in. This is going to make you cry. Always control latency. For those of you familiar with Netflix, Latency Monkey is the absolute worst thing to release on a system. It will bring your system to its knees. It is very hard to code and build a system that is resilient to unexpected latency. Scale horizontally. That's just almost always the right thing to do with Redis, is to just scale it out horizontally. Don't try to scale vertically. On modern machines, you will not use all of your resources. So it's a very inefficient, expensive spend to scale up vertically. And almost all the time, even with a couple of good just code libraries, you can hide all the complexity of having to split a large data set across multiple Redis instances. Monitoring tools are essential to when you start building out your clusters. If somebody has to it's very easy to add a shard in the wrong mode. It's very, in a stressful situation when your app is down, you need to bring up or rotate a shard. It's very easy to do the wrong thing if it's not completely automated. Connections tend to be expensive, particularly because Redis is single-threaded. It almost always, if you can spread a large number of connections across a large number of instances, you're going to see better performance. Redundancy and failover, automatic. Even in a 24/7 manned NOC, 10 to 15 minutes minimum to address. So that's how much data loss you're looking at, minimum. AOF is a fair weather friend. It's a really great way of getting a stronger level of durability, but there's generally, for that durability, you are trading off both performance and responsiveness in your system. So that's all I had to talk about today. We've got, looks about a little less than 10 minutes left. Questions? One in the back. So the RDB4, are you near your memory max on the box? That's probably your problem there, is because RDB does fork. So that means essentially a copy of the process's memory space. So if you're using RDB, you generally need to basically max out your memory at half of what the box can handle. Because you don't use, you turn persistence off? Yeah, that's honestly, I generally, just as a personal preference, I actually generally try not to use Redis where persistence and durability is extremely important. Yeah, was everyone up here kind of able to hear that? For the recording, essentially, there's a lot of things in this particular case with the RDB, both the settings, the Redis settings, the system and the memory that you need to look at. We had a really good answer from the back in case it didn't come through for the recording. But essentially, for posterity, go look on the web for more information. They're doing a recording, and it was a really good answer. I'm just not sure how much of it, it was a very good answer. I'm just not sure how much of it actually got onto tape. Honestly, it kind of is mostly dependent on your budget and your automation. I mean, honestly, once you have the processes fully automated, it's not that hard to build out more nodes. It's generally just kind of how expensive it is, budget-wise, whether it's AWS or whether it's hardware. Well, it depends. I would not put 1,000 nodes out, but I have built applications with 40, 50 nodes horizontally scaled, but those are independent. Generally, what we do is 2 read replicas or two replicas of each of those nodes. So it's 50, so 150 actual nodes. And then often on those boxes themselves, there's anywhere from 4 to 8 processes running. So I'm bad at math, but you can do the math. Generally, with the replication chaining, I generally only go 2. So essentially, I always look at 3 as kind of a magic number in systems, because then you can essentially tolerate 2 fails. So that's where I shoot towards, and that's worked well for us. I've never pushed it beyond that, so I don't know if, where really Redis is going to fall down, but that's a sweet spot that's worked well for me. Yeah, so in one of the systems we have, we actually use Sentinel for the failover. And then in another, which is actually a smaller cluster, we actually just use Twin Proxy and skip the Sentinel altogether. Yeah, if you have an answer, I've not found a good solution to that problem. What we ended up doing was using console and some scripts and basically hand-built environment-specific code to handle that problem. It's actually a really serious problem. It's one of the things I don't think this kind of failure is as mature. Obviously, I mean, Sentinel is quite new relative to Redis. I actually think this is there's a lot of work and improvement and just usability that could go into like a good failover solution for Redis. But we actually did not have a good solution for that. What we ended up building was trying to use console as a master record and then scripts on the box plus DNS switching to essentially point things around. I don't know of a good open source solution. So that's why I'm kind of pimping that. Like, this would be a great thing for someone to build as a project. Really build on the usability of Sentinel, because I think there actually, as you bring up, there are a lot of sort of additional operational concerns around Sentinel that the software doesn't address out of the box. I have mostly dealt with just asynchronous clients, primarily because any of the asynchronous operations, essentially, if you get a failure midstream, what do you do? You essentially, most of the asynchronicity comes from either like operation pipelining or some other crazy thing. Essentially, what happens if your operation fails? You're now in this odd state. So I've generally, just for correctness reasons, kept with synchronous clients. You can still do asynchronous operations over like a persistent connection with something like Twin Proxy. So you don't necessarily have the connection overhead, but you do. You can still get that parallelism or the asynchronous operations. And unfortunately, we're at the end of time, but we can talk more after. Thank you, everybody, for coming. I'm sorry we didn't get to all the questions, but I'll be available in the back if you have others. Thanks.